In this video, and I'm going to warn you, it's going to be a long video, we are going to look at line integrals. We're going to look specifically at scalar line integrals along a curve and vector line integrals along an orientated curve in space. And then we're going to use line integral to compute the work done on a moving object along the curve. And then we're going to talk about flux and circulation of a vector field. So this is a long one. I'll let you know right out of the gate, this will be long. So the first thing is we're going to talk about when we're doing integration in two-space. So when we're looking at two-space and we're doing integration from a to b of f of x dx, or even c to d of g of y dy, the domain of the integration is that a to b or c to d. And what we're doing is we're trying to think about how our curve is changing in the xy plane when I look at it along the line segment in either the x-axis or the y-axis. What we'd like to do now is we'd like to integrate over any curve. And to do that, we need to have a new kind of integral, and we're going to call it the line integral. Bam. This is like when we went from derivatives to directional derivatives. We wanted to be able to find the derivative along any vector. Now we want to do the integration along any curve. And like I said, when we started that, we're going to have two different types of line integrals. One is going to be the scalar, which is where we're going to start out first, and then we're going to do the vector line integrals. And what the scalar line integral is exactly that. They're integrals of a scalar function over a curve in a plane or space, and a vector line integral are integrals of a vector field over a curve or a line in space. So we're going to start with defining what a scalar line integral is, like we did with a single variable integration, except for now in a scalar line integral, the integrand is a function of more than one variable, and the domain of the integral is a curve in plane or space, as opposed to the curve on the x-axis or the y-axis. So let's start out with C being a smooth curve in space, and we're going to parameterize R of t, is going to be, and this is a vector, r of t, is going to be defined as x of t, y of t, z of t for in 3 space, where a is less than some t, which is less than some b. Let my function xyz be a function with a domain that includes the curve c. We're going to define the line integration of the function f over c. As we begin with most definitions, we're going to start with chopping it into small pieces, and we're going to partition a to b into n subintervals of equal length. Now, here's something that we want to point out. The partition length from A to B is the same length, but the curve may not be the same length. It depends on how the curve is formed. So if we take a look at this example, this picture shows that I'm looking at from A to B. This partition, when we partition this up, notice that these partitions are all the same, but the length of the curve from each piece is potentially different because the curve is changing, but the partition itself is, length of each partition is not. So that's one of the things that's different, which means that our regular Riemann sums needs to be altered slightly. And so the way that we're going to slightly alter it is we're going to say let f be a function with a domain that includes a smooth curve c that is parameterized by r of t as being x is a function of t, y is a function of t, and z is a function of t from a to b. The scalar line integral along c will be, notice that they have this little c as part of the integration of f of x, y, z ds, ds as being the arc length, the length of that arc. The length of the curve, the limit as n goes to infinity of the summation of f of each one of those p sub i's and the delta s sub i's. And we end up with taking the limit as we normally do, and we assume that the limit exists. Now, this is okay to do it this way, but it's also a little bit difficult to always be able to do this integration. So let's take a look at some of the geometry and then see if we can then readdress how we're going to find these integrations. So suppose we have this function down here, we have this function of xy is greater than or equal to 0 for all points xy on the smooth curve C. Imagine taking the curve C and projecting it upwards. So if we take a look at this, here's our curve C, and we've projected it upwards. And when we project it up, then the surface up here is going to be defined by f of x, y, where we now have this curve, we'll call it C prime, that lies in the graph of f of x, y. Now, if we drop, quote, a sheet on this, down onto the xy plane, this is our sheet that we drop on there, the area of the curve of this sheet is going to then be, as we've defined it, the integration of the line integral and the scalar line integral of f of xy ds. And as expected, what we would expect when we were just doing integration, if my function is below 0, then for some points of C, then those values will take on negatives. And so what that tells us is that our integration on the curve of f x y ds does not depend on the parameterization of r of t to c. So since we are able to do that, then we can then change the way that we address our limit stuff. So then we let r of t still be the vector r of t, y of t, z of t for all t between a and b, be the parameterization of the curve. We parameterize the curve. Since we are assuming that C is smooth, then the derivative of our parameterization of the curve is continuous for all t, and in particular that each individual derivatives must exist. So then if we have the appropriate arc length formula, sums, integrations, and limits, we can then say, oh, cool. Let f be a continuous function in the domain of the smooth curve C with a parameterization of r of t. Then I can integrate and find my line integral of f ds as from a to b of f of r of t multiplied by the magnitude of r prime of t dt. But since we know that r prime of t, the magnitude, is just going to be x prime of t squared, y prime of t squared, z prime of t squared, we can now do this replacement. So we can say, let f be a continuous function with a domain that includes the smooth curve C with the parameterization of r of t. Then my integration in 3 space or 2 space will take on these two formulas. And the knockdown result of these two theorems is that we can now think about the arc length as a change in the domain t scaled down by the magnitude of r prime of t. We're now going to look at 3 different integrations where they're asking us to find the scalar line integral, and the presentation will be different on each one of them. Our first example, I'm just going to go over all of them first. Our first example, it's already a vector f, and it's going to be the dot product of dr. So we're going to have to find the vector r and take the derivative of it. My second example is I have the function as x, y, and z, and I have the parameterization of x, y, and z, and that should be a space there, so z is equal to t. So I'm going to have to make this as a parameterization, this function as a parameterization, so that one will be slightly different. And this one is also slightly different because it's asking me for the scalar line integral of xy, and this should be dz, dz, xz, dy, and xy, dz. So each one of them are presented slightly different, but they're asking me to do the same thing, which is find the scalar line integral. So let's go to our first one, and it's pretty straightforward. I already have the vector f, so the vector f can be wrote as 0, -1. I want to find the vector r, so it's going to be a vector r parameterized, except for I'm not going to, well, I could change it to t, but I'm going to leave it with with x because I already have y in terms of x, so I can make the vector r as being x in terms of x, and then y as a terms of x would be 1/2 x cubed minus x. So now I've got a vector in terms of x. I still need to find the derivative because that's this part of it. So f r prime of x, so the derivative with respect to x, will give me 1,3/2 x squared minus 1. Now I'm going to integrate from, and since this is with respect to x, I only have to worry about this number and this number. So I'm from -2 to 2 of my f vector, which is 0, -1, with a dot product of 1,3/2 x squared minus 1, and dx, because everything's in terms of x. I could turn it in terms of t. That'd be totally fine to do that. And if I did that with a return in terms of t, it's not a big deal. It would just be x is t, and then y would be 1/2 t cubed minus t, and this would be in terms of dt. T, of course, because x is equal to t, would run between 2 and -2. So I don't necessarily have to do that. I'm going to do the dot product, and when I do the dot product, when I integrate from -2 to 2, and dot product will produce a scalar. And when I do the dot product, I'm going to get -3/2 x squared. And this becomes plus 1 dx. Now it's a scalar, so I'll change that to a scalar, parenthesis, instead of a vector. And I'm going to go ahead and integrate this like I normally do, and I end up with 4. This is still asking us to find the scalar line integral, but its presentation is slightly different. So first of all, I'm going to write x squared plus y squared plus z squared raised to the -1 as 1 over x squared plus y squared plus z squared. And now, because this is not a vector, and I'm not necessarily going to make this into a vector, I'm actually going to be using this other part, which is this one, is I'm going to then find the function evaluated with my r vector replacement and then take the derivative of the vector. So this then becomes x is cosine t, y is sine t, and z is t. So r, my vector r of t, would then be the cosine of t, the sine of t, and then t. So coming back to this replacement, I have 1 over cosine squared of t plus sine squared of t plus t squared. We know that this is equal to 1 all day long, so this is 1 over 1 plus t squared. Now I need to do the derivative of that, because if we look, using this other formula, it is my derivative of my vector t and the magnitude of it. So coming back down here, let me lock in my rotation again. Coming back down here, then I'm going to take this derivative. So r prime of t is going to be equal to, the derivative is going to be negative sine of t, cosine of t, and then 1. The magnitude of this vector t is going to be the square root of sine squared of t plus cosine squared of t plus 1, because 1 squared is just 1. As before, this equals 1, so this is going to be the square root of 1 plus 1, which is the square root of 2. So what I'm really integrating then is t is going to run between 0 and large t, so 0 to cap t, of my function replacement. So this would have been my function of r of t, and then multiplied by the magnitude, oh, that's not what I wanted, the magnitude of r prime of t dt. So this will be from 0 to t. My replacement, when I replaced my function in terms of t, is 1 over 1 plus t squared. And then, of course, my magnitude of my r prime of t is going to be the square root of 2 dt. Square root of 2 is just going to come straight on out because it's just a constant multiplier. And then we know that this is the tangent inverse, so it would be the tangent inverse of t, evaluated from 0 to cap t. So this is going to be the square root of 2, the tangent inverse of capital T, minus 0, so it's just going to be that. Now this is, again, something slightly different than the other two presentations. They're asking me to evaluate this scalar line integral over the line segment from 1, 1, 1 to 3, 2, and 0. So what I know is that r can be wrote as the vector p, which comes directly from here, plus t times the vector p to q. So this r of t, p can be wrote as the vector 1, 1, and 1. And this comes from earlier in our book, so Calculus 3 is where this comes from. And then plus t. To go from p to q, it's 3 minus 1. It's 3 minus 1, comma. And then it's 2 minus 1, so 2 minus 1. And then it's 0 minus 1. So this is 1, 1, 1 plus t, and 2, 1, and negative 1, which can be wrote because we can now combine these two up, this and etc., all the rest of them as well. This will be 1 plus 2t, 1 plus t, and then 1 minus t. So in this form, I know that x must be 1 plus 2t, y must be 1 plus t, and z, of course, would be 1 minus t. Now I have to think about how t has changed. Well, if t is 0 in each one of these, I get 1. Okay, so then I know where my starting point is t is greater than 0, but less than. I have to figure out how I got from 1 to 3, 1 to 2, and 1 to 0. Well, if I focus on this one, it's the easiest one. I would just say, okay, well, 1 plus t must equal 2, therefore t must equal 1. So I'm going to check that. If I put 1 in here and 1 in here, do I get 3 and 0? And the answer is yes. So I'm going to go between 0 and 1. So I know my integration is going to go from 0 to 1. So now how do I deal with all of this? Well, I know that my my y can be replaced by this, x can be replaced by this, and z can be replaced by that. So that's the easy part. So my y is the first one, so I have y, which is 1 plus t, multiplied by my z, which is 1 minus t. Then I have a dz. Okay, now what? Well, let's find dz and dt. Oh, no, I think that I have a sigh here because I believe my correction shouldn't be that. It should be, the correction should be, because otherwise I'd have two dz's and that would make no sense. I believe the correction should be, this should be z, and that one should stay as dx. Okay, so I have dx here. But let me find dx dt. But I can't just arbitrarily just say, okay, let's just change these dx dt, dy dt, dz dt, without putting a dt out front. Otherwise, we would have changed it. So then I'm going to continue doing the replacement. My next one is going to be plus x, which is 1 plus 2t, multiplied by z, which is 1 minus t. And this one is dy dt. And then plus, my next one is x, so it's 1 plus 2t. And then my y, which was 1 plus t. And this one is the dz dt. And if this all gets multiplied by dt, otherwise we would have changed the value. And you're thinking, well, what am I going to do with this dx dt? Well, I'm going to go back to these equations and do the derivative of each one of these with respect to t. So if I do each one of these with respect to t, this one is going to go here, and that derivative is 2. This one, the derivative is going to go here, and that's 1. And this one, its derivative is -1. So now I'm ready to actually do the integration. So my integration from 0 to 1 of 2 multiplied by 1 plus t, 1 minus t, plus 1 plus 2t, 1 minus t multiplied by 1, so I'm not going to write that. And then minus, because of the negative, so let me do a minus. And then minus, I have 1 plus 2t, 1 plus t, and this is all dt. Now I'm going to go ahead and find the answer. I'm just going to give you the answer rather than you watching me do it. And my final answer is -1. You all should go through that to make sure that I am giving you the right answer. Those were scalar line integrals because I ended up with dot products, or I ended up having to do something that would have produced a scalar I'm going to integrate over. Now I'm going to integrate over the vector line integrals, and there's a lot of applications for this. One of them is work. So we're going to integrate through a vector field where my vector field is going to be described as the vector f, x, y, and z, where p is a function of x, y, z in the I direction, q is a function of x, y, z in the j direction, and r is a function of x, y, z in the k direction. We assume it's going to be a continuous vector field in R3 that's going to represent a force on a particle, and c is a smooth curve in R3, and it's going to be contained within the domain of my vector field. To compute the work done by f by moving this particle c along a particle along the curve c, we need to determine the orientation. So now we really care about the orientation, how we go from one point to another. We didn't care about that with our scalar vector or our scalar line integrals, but we do care about that in vector line integrals. So the way in which we move is going to be our orientation. So this is an orientated curve. If my f of a equals f of b, so I go all the way around and I do a loop and I only do it once, then it's a closed curve. And what I mean by a and b is when I'm talking about a and b, it is in reference to my t, because I'm still going to have to do some parameterizations. That doesn't change. So my vector r of a, r of b, well, r of t is a parameterization from a to b. If I do this loop once and only once, transversed it exactly once, then we say that parameterization is 1-to-1 on that domain a to b. Now this is what we're doing. So we have these points. We on this curve. Here's our curve. Here's our vector field, and here's our tangential to some given point. We still cut them up into our usual smaller pieces. We still do the summations, and what we end up with is the work is equal to the vector line integral evaluated across this curve C, and we're going to have this f dotted with t being our tangential vector. And as before, we're going to try to make this a little bit easier to work with. So we go back to some of the ways that we described our tangential vectors. Then we end up with this. So f dotted with our tangential vector along the curve C with a arc length, or our length of our curve ds, can be wrote from a to b of f evaluated at our parameterization r prime of t dt. And the way in which we're going to see the notation will be slightly different at times. If I am going in the other direction for my parameterization, that it would be negative c, which can be noted as a negative out front of our integral. And this kind of makes sense, because if we think about the line integral as finding the work, then if you hike up a mountain, the gravitational force is negative work on you. If you walk down the mountain, the exact same path, then the gravitational force does positive work on you. So in other words, reversing the path changes the work value from a negative to a positive. And that's why we see it in this, something noted like this. And so we end up with our function f, so to make everything a little bit easier, Our function f dotted with our derivative dr can be wrote in this form, which means we can do our partial derivatives, which means the end result is this. I can evaluate my p function with my replacement of the r parameterization vector and then take the derivative with respect of x with respect to t. Q, dy dt, r, dz dt. It just makes it a little bit easier. So let's take a look at our first example here. We have our vector field, which is only in 2 space, and our curve is y is equal to x cubed. I'm going to go from 0, 0 to 2, 8. So this was like our first original scalar vector that we did before, is it's already kind of got the vectors. Of course, x is equal to x, y is equal to x cubed, and then our r of x, in this case, will be x comma x cubed. Now, if I take this derivative with respect to x, so r prime of x, will give me 1 comma 3 x squared. Now, I am integrating on a vector, and this vector is not a constant vector, so I'm going to integrate from. And my x's is what I'm doing in this respect to it, so it's going to go from 0 to 2. So 0 to 2. Of my vector f, well, I'm going to rewrite my vector f of x comma y as negative x comma negative 2y. So this then becomes, here, is going to be this vector. But remember, I don't want to have to do this integration twice, so I'm going to do a replacement that my y gets replaced with x cubed. So then this f of x comma y is going to be negative x negative 2x cubed. Okay, so I have negative x negative 2x cubed. That is my f, my vector field, multiplied by the 1 3x squared. Still a dot product, but notice on this one we had to do some replacements. Now, when I do this dot product, of course, it's going to be a scalar, and I end up with from 0 to 2 of negative x minus 6x raised to the 5th dx when I do the dot product. And when I get totally done, I get negative 66 units, whatever the units are, of work. Now let's take a look at my next example here. We have f of x y is going to be x squared plus 2x e to the y plus 1 in the I direction. We have 2xy plus x squared e to the y plus 2y in the j direction. And I've got my parameterization already done for me. It's r of t is equal to sine of t cosine of t in the I and the j direction, respectively, from t going from 0 to pi over 2. So I can go right to my derivative of my r vector with respect to t. Now I'm going to write it in vector component form. And the derivative of sine is going to be cosine. And then the derivative of cosine is going to be negative sine. Nothing surprising there. The most interesting part is it going to be doing these replacements in terms of these here. X clearly is going to be the sine of t this time, which is not usual what we get. And my y is going to be the cosine of t. Normally we have those switched, but no, spice it up this way. So wherever I see y squared, this function, this vector of x comma y, wherever I see y squared, I'm going to replace with cosine squared of t, plus 2, x gets replaced with the sine of t, e raised to the cosine of t, plus 1. That's just in my I direction. And then in my j direction, I'm going to have 2, the cosine of t, the sine of t, and then I'm going to have plus, there should be a comma there, should be a plus, and then x squared is sine squared of t, e raised to the cosine of t plus 2 the cosine of t. So that's my vector f with that parameterization. My integration is already set up for me. I know my t is going to go from 0 to pi over 2, and then it's going to be the dot product of cosine squared of t plus 2 sine of t e raised to the cosine of t plus 1, 2 cosine of t sine of t plus the sine squared of t e raised to the cosine of t plus 2 cosine of t, and the dot product of that with the cosine of t, comma, the negative sine of t, dt. Lot of math going on. So this entire thing is going to be multiplied by the cosine of t, and this entire thing is going to be multiplied by the negative sine of t. And when we finally get done with a whole bunch of cleanup and some integration that's going to happen, we totally get done and we get 1 is the final answer. Of course, I will go through this in the classroom if you want, but don't want to muddy up this video for you watching me doing the multiplication and the integration. Let's take a look at my last example. Well, actually, no, I think I've got, my last example before I go piecewise. Let's zoom in on this one. So here's my function, or here's my vector field. I'm going to rewrite it as 12x squared minus, or comma, negative 5xy, comma, xz. I just like that better. And notice that my y is in terms of x, my z is in terms of x. So then my curve, my r of x, I'll do this with respect to x, my vector r with respect to x would be x, x squared, and x cubed. So I don't always have to parameterize with respect to t. I can respect to x, which is kind of nice. So then when I do this integration, I'm going to have the integration from 0 to 2, because I have this x's in terms of, everything's in terms of x's. Now my function, my vector field, I should say, is going to be 12x squared. Negative 5x, y gets replaced with x squared. And then x and z gets replaced with x cubed. And then I have x squared, x cubed, dx. And I do this dot product. And I'm going to end up with, from 0 to 2, of 12 x squared minus 10x to the 4th plus 3x to the 6th dx. Nice, easy integration. And I end up with 160 over 7 when I get done. Units of work, whatever that happens to be. Now, piecewise. You're all like, cool, I loved piecewise. Said no one. I know what you all are thinking. I didn't enjoy piecewise when I learned it the first time in Pre-Calculus 1. I didn't like it when we were in Pre-Calculus 2. I still didn't like it in Calc 1, 2, and 3. Well, here it is in Calc 4. Maybe now you'll really like it. So, C is an orientated curve. Not necessarily smooth, but can be written as a union of finitely many smooth curves. Then we say that C is a piecewise smooth curve. So in other words, say I go from here, this point, to this point, and then to this point, to this point. It's a piecewise smooth curve, even though I have kinks in here, because I can think of it as these connections of all these curves. As long as I can get from one point to the other point to the next point without picking up my pencil when I'm drawing the path, then it's considered a piecewise smooth curve, which gives us these properties. let's talk about these properties, what each and every one of these properties are. This first property is similar that we would expect when we're looking at regular single variable integrals, that if I have these two vectors, vector fields f and g, dotted with dr, then I can break them apart with addition. This second one is just like we would expect in, again, our single variable integrals, is that I have this constant k can be factored out. This is similar to, again, when we're thinking about from a to b in our single variable, and we want to switch it to from a to b and then switch it to b to a instead, that we would have the negative out front. So if I want to go in a certain direction, this negative in the negative orientation, so if we want to think about going through the curves, instead of going in this direction, if I wanted to go in this direction, then all I have to do is say I'm going to go in the negative and I'm going to put a negative out front. And then this last property is why we care about the whole piecewise, right? So suppose instead C is a piecewise smooth curve in the domains where I have f and g, and I have my curve can be broke up into individual pieces. That means I can do individual integrations on each piece of the curve as long as I'm able to draw from one end to the other without picking up my pencil. So let's take a look at what that does for us on this example here, where I'm going to find the work done on the vector field. C is counterclockwise. I'm going to go around these vertices. So here's my picture. I'm going to go from 0, 0, then I'm going to go to 1, 0, and then I'm going to go up here to 1, 1, and then I'm going to go back to where I started. And it is a counterclockwise, so I've got my motions in here. So my work on my curve C of f dot dr. Let's go back to our drawings. This is the line y is equal to 0. This is the line x is equal to 1. And this is a line y is equal to x. So when I break this up in my orientations, and here's my f, which is 2x comma y. We'll start with this line y is equal to 0. So we'll start with this first curve. So from y is equal to 0, x is going to go from 0 to 1 of my vector 2x, and y will be 0 because I'm not moving along the y in any direction because I have y is equal to 0. It's telling me y is equal to 0. And then it's going to be dx, because the thing that's changing is dx, and then 0. And my green line, it's going to go from 0 to 1. This is the line x is equal to 1. So I'm going to have x is equal to 1 right here. So I have 2 times 1 and then y. And then 0 is not, or x is not changing. X is a constant, 1. The thing that's changing is dy. And then in my red line, well, my red line is going to go from 1 to 0. So I start out to 1 and I go down to 0 of 2xy dx dy. Now, what I want to do is I want to avoid this last one as being two variables. So this is the one I'm going to parameterize. So this, I know that, well, x is equal to y. So I'm going to change this into 2x comma x, because x is equal to y, and then dx dx. So what this is now equal to is my 0 to 1 of 2x dx, that's the blue one. It's the blue. And then plus my green, which is going to be from 0 to 1, of, well, when I do the dot product, it's just going to be y dy. That was my green one by the dot product. And then my red one, so plus, from 1 to 0, of my red one was going to be, the dot product here is going to be 3x dx. So when I integrate all of this, and it has to be 1 to 0 because I start at 1 and I go to 0, I end up with 0. That's my final answer. You all should check that just to confirm. And of course, it's units of work. Units of work. No work done. Ha, ha. Never mind. Anyways, let's take a look at our next one. We are going to find the work done in this vector, y squared plus 2yx plus 1 in the ij direction. Notice that there's no k, but it's still in terms of x, y, z, and that's totally fine. So our vector field is going to be y squared 2yx plus 1. We're going to go from 2, 0 to negative 2, 0. And we're going to go counterclockwise along this ellipse. Now this is an ellipse. Let's put this in the standard form of ellipse. So it'd be x squared divided by 4 plus y squared divided by 1 is equal to 1. That's what this is as an ellipse. That means I would go out 2 each direction in the x direction and 1 in the y direction. So it's going to look something like this. This is our ellipse. And we're going to go from 2, 0, which is right here, and then we're going to go to negative 2, 0. So we're going to go in this direction. So we always want to know which direction we're going on. And then back to, well, then we're going to go back to our 2, 0. Ooh, helps if I pay attention. Along the x-axis. So along the x-axis. All right, so let's dig in deeper. Let's go ahead and parameterize our curve. This is our curve. So let's parameterize our curve in terms of t. And we know that we can replace x with r cosine t anytime that we want. So in other words, my x can be replaced with 2 cosine of t because of that 4 down below. And then my sine is just going to, my y is just going to be the sine of t. So I've now got my r of t in terms of x and y. So that means I'm going to go in, it's going to go from 0, starting from 0 to pi, back to 2 pi. So even though we're going along the x-axis, that's okay. My integration is going to go from 0 to 2 pi. And as before, I need to find my replacements of my function here in terms of my parameterizations. Y gets replaced with sine of t, and x gets replaced with 2 cosine of t. So my f function becomes, as vectors, becomes sine squared of t, 2 multiplied by the sine of t, and then 2 cosine of t, and then plus 1. So this is f of r of t. These are vectors. And then in this form, remember, I'm going to take the derivative of my r of t. So my derivative of r of t is going to be negative 2 sine of t, cosine of t. This is r prime of t, dt. I'm going to do the dot product like I normally do. And when I do the dot product from 0 to 2 pi, I'm going to end up with, and you all should check this by doing it yourself, is I'm going to get the negative 2 sine of t plus 6 6 sine of t cosine squared of t plus the sine of t cosine of t dt. Now I can break this apart and factor out of these two. I can factor out a sine of t and then do some u substitution stuff. But at the end of the day, when I get totally done, my answer is 0 units of work. And you all should, of course, check that. There are real applications to line integrals. One of the things that we get from the scalar line integral, we can find the length or mass of a wire and the surface area of a sheet of a given height, or the electrical potential of a charge of a wire given the linear charge density. Vector line integrals we can use to find work done on a particle as it moves through a force field, or the flow rate of a fluid across a curve. It's going to be really important later. Here's an example. A thin wire is bent to the shape of a semicircle of radius a. If the linear mass density at point P is directly proportional to its distance from the line through the endpoints, find the mass of the wire. Well, the first thing I'm going to do is draw a picture. So we have this semicircle, and we know this is the point 0a, and this is the point, of course, a comma 0, and this is the point negative a comma 0. The curve is, of course, something of the form x squared plus y squared is equal to r squared. So, of course, our r vector in terms of t would make sense to use a being our radius, cosine of t, and a sine of t, because we know that we have a radius of a. So that's nothing surprising. That should be a vector. Let me change that to make that a vector instead of a parenthesis. Vector. And of course, we can see that I'm going to start at 0 and I'm going to end at pi for my t. So 0 to t to pi. Those are some terrible inequalities. Now, if the linear mass density at point P is directly proportional to its distance from the line through the endpoints, well, here's the line through the endpoints. It's the x-axis. This is the distance. It's y on the xy plane. So my integration then is going to be over my curve C, rho, my density, ds, which in this case is going to go from 0 to pi of k multiplied by y. And then I would multiply this by the magnitude of my derivative of my vector r dt. So this is going to be equal to, from 0 to pi. Now I've got to replace my y with, so I have k, multiply my y with a sine of t, and then the square root of, well, I have a cosine squared of t. That's my derivative of, actually it'd be sine first, but it'll all work out. So the derivative, my vector r derivative, is going to be negative a sine of t, a cosine of t. So this is going to be a squared, the sine squared of t, plus a squared, the cosine squared of t, dt. And of course, we know that we can factor out an a squared, then we just have sine squared plus cosine squared, which is just 1. And so I'm going to have this integration from 0 to pi of ka, the sine of t, and the square root of a squared dt. But a is not dependent on t, so the square root of a is just a. K is not dependent on t. So I can factor out an a squared times k from 0 to pi of the sine of t dt, which, when I integrate this, is a squared k. Integrate the sine, I know I'm going to have the negative cosine of t, evaluated from 0 to pi. And my final answer, when I get done, is going to be 2 ka squared, whatever my mass units are that are appropriate to this example. Let's take a look at the next example. We have a spring is made of thin wire twisted in the shape of a helix. Find the mass of 2 turns of the spring if the wire has a constant mass density. We know that my R vector parameterization is going to be the x part, which is 2 the cosine of t, 2 the sine of t, and then t. And of course, we're going to take the derivative of this. R prime of t is going to be negative 2 sine of t, 2 cosine of t, and then 1. And we're probably going to find the magnitude. That's what you're thinking. I'm thinking you're right. So that's going to be the square root of 4, the sine squared of t, plus 4 the cosine squared of t, plus 1. Factoring of 4 out of the first 2 terms gives me a sine squared of t plus cosine squared of t, which is just 1. So this is going to be the square root of 4 plus 1, which is the square root of 5. So we've done that part. Now, our rho is a constant, so our mass is going to be the integration across C of rho ds, which we're going to do 2 turns, so it's going to be 0 to 2 pi of my rho, which is a constant, so I'm just going to pull that out front, and the square root of 5 dt, which, when we get done, is just going to be square root of 5 rho t evaluated from 0 to 2 pi, which gives me a final answer of 2, the square root of 5 pi rho, whatever my units are, my units of mass. And that's pretty much it. We have 2 more things to cover in this section. Like I said, I warned you at the beginning, this is a long video. We have flux and circulation. So let's talk about what flux is and let's talk about what circulation is. And it's not the flux capacitor either, if that's what you're thinking. Flux is used in applications to calculate the fluid across a curve. Now, what we want to think about this is we have this membrane, but it's totally permeable, and it's not going to impede the flow, but it is going to be able to determine how quickly the flow rate is. And that's what flux is how fast is this moving across some curve. But the curve is not impeding the flow at all. It's just basically like checking maybe how fast the air is flowing, how fast the river is flowing. So what we're doing then is we're actually looking at the normals on the curve. So we're finding the vectors normal to the curve. Here's our curve C. Here's our flow rate of our vector field. And so we want to know what this normal is. So we'll need this normal vector. And what we end up with is the way that we define flux is going to be my F with my parameterization of R, as we normally expect, and then my normal, which, if you remember, the tangential vector would have been the partial derivatives with respect to x and y, and then the normal must be the partial derivatives with respect to not x and y, but the positions will be switched, and one of them will own a negative. By convention, we usually have the negative on the second one, but it doesn't really matter. Sometimes you might see it noted as this. So we have the flux is written as negative q dx plus p dy here. Because the normal unit vector is perpendicular to the tangential vector, then dr becomes dx, dy becomes dy dx with a negative on the dx by convention. So we want to find the flux of this vector field across this line segment. So the first thing we got to do is figure out what the line segment is. Got to find the slope. So the slope of the line. We're going to go from 2 minus 0 and then the 1 minus 0, so we have a slope of 2. Goes through 0, 0, so the equation of the line is 2x. So then my curve is going to be r of t. Of course, it's easier to just write t as x. So if t equals x and x is equal to t, then y is equal to 2t. So I've got t, comma 2t. Because y is equal to, or excuse me, t is equal to x, I'm going to go from 0 to 1. So 0 is less than or equal to t, which is less than or equal to 1. And then my normal of t is going to be the derivative of my r vector. In fact, let me do it this way. I'm going to do my derivative of my r vector. R prime of t is going to be 1 comma 2. So then my normal will be 2 comma negative 1. Nice. My function, which not my function, by my vector field, is x squared y. And with my replacement of x is equal to t, this becomes t squared, y is t. So now I'm ready to do my integration for my flux. I'm going to call my phi function as my flux. And so I'm going to integrate for t, which is from 0 to 1, of my vector t, or my vector of my field, my vector field, in terms of t, will be t squared and t, dotted with the 2, negative 1, that's my normal vector, with respect to t, which is equal from 0 to 1. When I do this, I'm going to get 2t squared minus 2t dt. And when I integrate this, and you'll notice that a lot of these integrations are pretty straightforward. They're not like some of the integrations we've done where we're like, I'm going to have to put this in polar. No, it's not too bad. And I end up with negative 1/3, and then whatever my units are for flux. So it could be cubic feet per minute. Depends on what my units are. So flux units. Okay. Let's take a look at this next example here. We're going to go in a counterclockwise. We're going to go across x squared plus y squared is equal to 9. And you're thinking, oh, a really good choice for the parameterization for r of t would, of course, be 3 cosine t, not cotangent, cosine of t for the x, and, of course, 3 the sine of t for the y. Good choice. Which, of course, it's a circle, so, of course, my t would go between 0 and 2 pi. That takes care of that. Let's go ahead and do my derivative, r prime of t, which is going to be negative 3 sine of t, 3 cosine of t. That means my, should have been a vector up there, my vector, normal vector, is going to be 3 cosine of t, negative 3 sine of t. So that's easy peasy lemon squeezy. Now we have to do the replacements. My field, in terms of x and y, is x squared plus y cubed, comma, 2xy. So parameterizing this, I'm going to get 9 cosine squared of t plus, I'm going to get 27 sine cubed of t. And then I'll have 2 times 3 cosine of t, 3 sine of t. So now I've parameterized this as f of r of t. Now I'm ready to do my integration. So my integration, because it's now in terms of t, is going to go between 0 and 2 pi of the vector 9 cosine squared of t plus 27 sine cubed of t, comma, 2, well, actually, I'll go ahead and do this multiplication. It'll be 2 times 3 times 3, so it's 18. Cosine of t, sine of t, dotted with the 3 cosine of t minus 3 sine of t. dt. And when I multiply this out and combine up like terms, I'm going to be able to factor out at the very end 27, 0 to 2 pi. And this ends up becoming the cosine cubed of t plus 3 cosine of t sine of t cubed. So that sine is cubed. That's a terrible cubed. So cubed of t plus 2 the sine squared of t cosine of t dt. With the appropriate substitutions and all the shenanigans that ends up coming out, I end up getting 27 multiplied by the sine of t plus 3 sine to the fourth of t divided by 4 plus the sine cubed of t divided by 3 evaluated from 0 to 2 pi. And we know that when we're looking at sine of 2 pi or 0, that's 0 all day long. Each one of these are a sine of t, so the answer is 0. So that tells me that my flux, whatever my units of flux are, is 0. I have nothing coming in or going out. It's going to be equivalent. So whatever's coming in is going out. So this is units of flux. All right. Last thing is circulation. When the line integral of the vector field f is along an orientated closed curve, then it's called circulation along C. It is noted with this circle on my integral in my integrand C f of t ds. And it is measures the tendency of the fluid to move along the direction of C. That's like, I always think of the lazy rivers, you know. And anyways, of course, with the negative, we get this, and we get negative 2 pi, so that's kind of cool. Find the circulation around this closed path consisting of each one of these pieces. I already have the r of t for each one of the 3 pieces, so this is a piecewise, so it gets our piecewise in here. And I've already got the initial replacements. So let's start with the first one, C1. So C1. I have r of t, which is, of course, the cosine of t, the sine of t, and then t, so it's a nice helix between 0 and pi halves. Now we've got to think about what happens to our function on this. And our function starts out with an x, y, and z is going to be equal to 2x, 2z, and 2y. So f over this r of t for just the C1 will equal 2 cosine of t, 2t, and then 2 sine of t. All right. So, of course, I'm going to need my derivative here. Should have done my derivative r prime of t. It's vector r, which is going to give me negative sine of t, cosine of t, and then 1. So now I'm ready to do this first integration. So I'm going to integrate from 0 to pi over 2 of my f of r of t, which is 2 cosine of t, 2t, 2 sine of t, dotted with the sine of negative sine of t, cosine of t, and 1 dt. And I would do the same thing for my second one. So C sub 2. My r of t is given as 1 pi over 2 comma, well, multiplied, should be a comma, multiplied by 1 minus t. And then, oh, my I is, pay attention, my I is 0. So this will be 0. And then I have pi, or my j is 1. So 1, and then my last one, k, is pi over 2, 1 minus t. So then I would do my f and the r of t. Don't forget my derivative. So I need my derivative r prime of t, which is going to give me 0, 0, and negative pi halves. When I do this replacement, my x is 0, so this will be 2 multiplied by 0. My y, my middle piece is 2z, so this will be pi divided by 2, 1 minus t. And then, oh, don't forget to multiply that by 2. And then my last one would be 2 multiplied by 1. This goes from t, so t is going to run between 0 and 1. So this integration is going to go from 0 to 1 of my 0 pi multiplied by 1 minus t, and then 2 dotted with 0, 0, and negative pi halves dt. And then I would do my last one, c sub 3. In this case, it would be r, zoom this out, r of t is going to be 1, and then, let me see this middle one, 1 minus t, and then 0. R prime of t is going to be 0, negative 1, and 0. My f, r of t, is going to be 2 multiplied by my x, which is 1, 2 multiplied by my z, which is 0, and then 2 multiplied by my y, which is 1 minus t. This t is going to go between 0 and 1 as well. So this integration is going to go from 0 to 1 of 2, 0, 2 minus 2t, dotted with 0, negative 1, and 0, dt. And I would add up each one of these. So I have this first one, I have this second one, and I have this third one. It's a nice piecewise. So I would integrate 1 and add it to the integration of 2 and add it to the integration of 3. And when I get totally done with everything, I end up with 0. Now each piece is not 0. The flow of the first one, the flow of the second one, the flow of the third one, all of those flows added up together ends up giving me 0. And that's it for this video. Like I said, it is a long one. I'm going to spend some quality time on it this week. We'll see you in class.